How do we predict what's coming next? No, not with a crystal ball. We use data. You see, the world leaves behind this trail of clues, these little data points recorded over time. And the real trick is learning how to read that trail to make a clear, calculated forecast about the future. Just think about some of the most important data we track. Stock prices, right? They're a constant stream of information, changing literally every second. Or how about a company's sales figures? Those are usually recorded every month or every quarter, and they create this really clear sequence that businesses absolutely rely on to plan ahead. Even something as natural as weather patterns. Daily temperatures, monthly rainfall, it's all recorded in a sequence. Every single data point is a piece of evidence left behind by the past. So the big question is, how do we follow this trail of clues to predict what's going to happen next? Well, that's exactly what we're going to dig into. Today, we're officially opening the case file on time series forecasting. Let's treat this whole thing like a detective story. The mystery we need to solve, it's hidden right there, inside the data. So our very first step is to understand our primary piece of evidence. In our investigation, this time series is basically our crime scene. It's the official record of what actually happened. Now, you can think of some underlying random process as all the possible ways things could have happened. But our data, our time series, that's just one of those paths. Our job as detectives is to analyze this one single crime scene to figure out the rules that govern the entire mystery. Okay, so for any good detective, the #1 rule is to make sure your evidence is reliable. In time series, this means our data has to be stable, or what people in the field call stationary. And let me tell you, this is the most crucial step of all. Just look at the difference here. On the left, you've got non-stationary data. This is our unreliable evidence. Its basic properties, like its average, are all over the place. It might have a trend shooting upwards, making it totally unpredictable. But on the right, you see stationary data. It's stable, it's reliable, its statistical heartbeat is constant. This is the kind of evidence our forecasting models need to actually work. So how do we even check if our evidence is reliable? We use a tool called a unit root test. Think of this test like a police interrogation. It starts by assuming the data is guilty of being non-stationary. That's its null hypothesis. It assumes our data is just wandering around aimlessly, kind of like a drunkard's walk. Our job is to find enough proof to show that assumption is wrong, and that our data is, in fact, stable and trustworthy. You know, the process for stabilizing our evidence is actually pretty simple. It's a 3-step mission. First, we run that unit root test. If the data fails, if it's unstable, we move to step 2 and apply something called differencing. That sounds fancy, but it just means we calculate the change from one point to the next. That simple move usually gets rid of the trend. And finally, step 3, we test it again to confirm our evidence is now stable and ready for analysis. All right, our evidence is stable. We can finally trust it. Now that we're not chasing a moving target anymore, we can pull out the magnifying glass. It's time to start looking for those hidden patterns, the fingerprints, inside the data. Our main tool for finding these fingerprints is autocorrelation, or ACF. It's a really simple but super powerful idea. We're basically measuring how much today's value is influenced by yesterday's value, or the value from last week or last month. The plot this creates is like a DNA test for our data, revealing its internal memory, its whole family history. And this table right here, this is our decoder ring. By looking at 2 different plots, the ACF and the PACF, we can identify the data's unique signature. Check out the patterns. If the PACF plot on the right shows the correlations suddenly dropping to 0 after a few steps or lags, that's a dead giveaway. It's the fingerprint of an autoregressive process. But if the ACF plot on the left is the one that cuts off sharply, that's the signature of a moving average process. This little cheat sheet tells us exactly what clues to look for. So we found our clues in the ACF and PACF plots. Now we can finally put the pieces of the puzzle together and build a profile of the process that created our data. In other words, we get to identify our model. If our clues pointed us to an autoregressive model, or AR, it means our time series is driven by its own past. Think of it like an echo. The value today is a direct result of the values from yesterday and the day before, and so on. The strength and the length of that echo is exactly what the model captures. Now, if the clues pointed to a moving average model, or MA, the story is a little different. Here, the current value isn't based on past values, but on past errors or random shocks. Imagine tossing a small pebble into a calm pond. The state of the water right now is influenced by the ripples from that past event. An MA model captures how long the ripples from a past surprise actually last. But in the real world, a lot of time series have a bit of both. And that's where the ARIMA model comes in. It's the powerful, all-in-one model that combines the echo of the AR model and the ripple effect of the MA model. And that I in the middle, it stands for integrated, which is just a nod to the differencing step we did earlier to make the data stationary. And this is where our whole investigation comes together. The ARIMA model is defined by just 3 numbers, P, D, and Q. P tells us how many past values, those echoes, are important. D tells us how many times we had to difference the data to get it stable. And Q tells us how many past shocks, those ripples, are still affecting things right now.
So, we've done it. We've gone from a mysterious set of random-looking data points to a fully specified model that explains its behavior. Now it's time for the final step, using that model to predict the future.
So let's just trace our steps one last time. We started with the raw evidence, the data. We stabilized it to make it reliable. We used our tools, the ACF and PCAF plots, to find the critical clues. Those clues let us build a profile of our suspect, the ARIMA model. And now, that model gives us everything we need to forecast what comes next. And really, that's the power of time series forecasting. It's this structured, logical process. It's not magic, right? It's about methodically uncovering the hidden structure in our historical data to create a reliable guide for what lies ahead. We build a model of the past to help us navigate the uncertainty of the future. And that's the whole framework. It's how data detectives solve the future. From the absolute chaos of the stock market to the predictable rhythm of seasonal sales, the process is always the same. The clues are always there, just waiting in the data. So now you have the keys. The only question left is, which mystery are you going to solve first?